Welcome. I'm looking at quadratic cohomology again. I mentioned already in spring this fusion inequality which parallels the fusion inequality in the linear case. The linear case is simplicial cohomology, where you look at functions on the simplices themselves. So this is encoded by a finite set and the n elements and the n times n matrix, which encodes all the exterior derivatives and then the dimension function, which is necessary if we look at the cohomology in an open set. Open sets are defined once we have this topology generated by the stars of the simplicial complex. This is a non-Hausdorff topology if the dimension is positive, and then we can look at an open closed pair, which is very exciting. Think about G as the world, K as the laboratory, and U the environment. Now, in the simplicial cohomological case, there's still there's an inequality in general, not the equality here. Unlike for the f vectors, we see here the f vectors in an example, the f vectors always add up, right? We can look at the elements in the open set, the elements in the closed set, and they should add up to the elements in G. That's just because we have a partition. Now, in the case of quadratic cohomology, we look at functions on pairs of simplices which intersect. So this is, as far as I know, a new cohomology which has not been considered in the continuum, because in the continuum we cannot access the individual atoms of space, right? We have here just a nice feature. We can just look at the exterior derivative which comes like we would have on a product space, but we only look at the parts where we have an intersection. Now we have also for U, we can look at all the pairs of U, where the intersection is in U. We can look at all the pairs where the intersection is in K. It cannot be in U, right? If you take two elements, two simplices in K, their intersection is in K by the definition of an abstract finite simplicial complex closed under subset operation. Now we can also look at pairs of either X is in U and Y is in K, and here X is in U and Y is in K, or we can look at X in K and Y in U. So this is, and then there is another possibility which I missed actually early this year, and it was very frustrating because there are some cases which I did not expect to occur, like if X is in U and Y is in U, where the intersection is in K. So that's illustrating here. X is in U, Y is in U, and X intersected with Y is in K. This looks impossible, but already here we have an example, right? We have that if you take here X and Y, they are both in the open set. I took here just an example where I took a closed simplicial complex, which is just a K2 subgraph here, and that it, of course, this defines a simplicial complex, subsimplicial complex, which is a closed set, and the complement is an open set also by definition. And so the X, this triangle and this triangle, both of the triangles are in the same open set, but the intersection is in K. So that's they are more interesting interactions. And if you keep track, so there are 5 possible cases of interactions. There are 3 cases which don't occur, right? There are 8 total cases. Right? X in U or K, Y in U or K, X intersected with Y in U or K. So there are 3 cases don't occur. There's an asymmetry between closed sets and open sets. And here we have the 5 cases which occur, and this keeps track of that. If I would replace B with F, the F vector, then it would be an equality, because we just keep track of the individual pairs of simplices. So we look in which case we are. So that's simple counting. And then, of course, also for the characteristic, this is Euler characteristic, this is Wu characteristic, Euler characteristic, this adds up, right? If you add up the Euler characteristic of U and K, you get the Euler characteristic of G, because it's just a partition. And here also we have the Euler, if you add up all these Euler characteristics, we get also the same. And also for the F vectors, you can see the F vectors add up. And the F vectors here of the This is the linear case. This is the quadratic case. The quadratic case is much more interesting because we can have intersections of points with points, points with edges, edges with edges, triangles with points, or edges with edges. So we have lots of different possible triangles with triangles. Right? We have all these cases which we can consider, and each of these cases produces a cohomology, which is a topological invariant. It's relatively easy to see why it's a topological invariant. If you take a ball and you just look at gauge the thing so that the equivalence class is 0 in that ball, then you can replace the ball with some other ball, and then you let the heat flow again produce a harmonic form. So you can these cohomologies are all topological invariants, which is very, very exciting because, for example, we can take K, a sub closed simplicial complex, which could be, I'm actually more excited in the case when U is the level surface, right? U, the open set, is a level surface. If you look at the SAR theme, which I talked a lot about early this year, when you look at level surfaces, like the intersection of two level surfaces is a curve in three-dimensional space, right? Which is a manifold, always or empty. It's always a manifold or empty, and so it has to be a link. Finite union of knots. And then you can look at what happens with these cohomologies. These are topological invariants. So it's potentially very, very interesting, but this is just the beginning. I really only started looking at this, and one of the first steps is to understand the Betti vectors, what happens with the Betti vectors if you do this fusion. Now, what happens here in the linear case, the proof is actually just a spectral proof, because the cohomology is defined spectral in a spectral way. The harmonic forms of the K Laplacians are this is the case cohomology. And so if you have 0 eigenvalues in G, so you have also then eigenvalue 0 in K or U. And so that produces you this inequality, and the proof is the same, it's just the matrices are much more complicated. By the way, I will post the code. It's a little bit longer than in simplicial cohomology. The quadratic cohomology code is similar, but I have here things implemented in Mathematica, and it produces these two tables are just computed. You take a random complex and a random sub-complex, and you get the numbers. If you can compute it, the numbers, the matrices, of course, are getting very, very big. You can see this here already, kind of 40, 73 plus 8, 81 times 81 matrix for that G. You have to consider when you want to compute the cohomology of G, or each of these matrices, right? You look at each of these matrices, and you look at the kernel of these matrices. But it's very down to earth. Everything is finite. They are finite. It's linear algebra. And especially nice that here Cauchy interlacing theorem enters in a nice way to prove these inequalities. That's it for today.
You want to leave this place where we grew up, this old town, just put it all behind. Remember you and I would always find somewhere to hide when we were kids, so we could see and hear the water run. The river's gonna cry when you're gone. You miss the ones you know. I'll be here, hanging on, waiting for your call. Seems like time as a wave passing by, leave a mark in our minds to turn to memories. River's gonna cry when you're gone, 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 gone. River's gonna cry when you're gone, 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 gone. River's gonna cry when you're gone, 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 gone. River's gonna cry when you're. River's gonna cry when you're. River's gonna cry when you're gone.